This is project 6 video number 3, the one in which we do the documentation and finishing touches. I feel like getting the graph right first, so I'll title the graph, and I want to go with it's a graph of electric field due to a uniform ball of charge. And we'll see how that comes out. I might have to shorten it, but where are we at? X label. It's EL. Along X, I'm plotting little r, and I go distance out from center of ball of charge. And once again, if that's too long, I'll fix that up. I'm going to put units meters, and then Y label. I'll put magnitude of electric field, and I want it in units of newtons per coulomb. And let's go ahead and try saving that, see what that looks like. Need a close apostrophe there. Try Control S to save it. Run it. And I think it looks alright there. So electric field due to a uniform ball of charge. Magnitude of electric field in newtons per coulomb. Distance out from center of ball of charge in meters. That's my little r. I think that looks perfect. So back to the editor. Go attribution. Write the story of how your function came into being here. So what I'm saying is to write it here, not how it came into being at this location. Okay. Here, percent, this function makes a graph of the magnitude of the electric field due to spherical charge distribution of radius r, for which the charge is uniform. A uniform spherical charge distribution of radius r as a function of the distance out from the center of the sphere of charge from the center itself out to 3 times the radius of the ball of charge. So say what the situation is and what this function does here, and then I go percent input variables. These are the function arguments. Percent capital Q, say what it is. Percent capital R, say what it is. Then percent, there are no output variables. Then don't forget to put your name on this. So we're going to go percent by Jeffrey W. Schnick. And alright. Distance out from the center. So that's what R is, and then assuming somebody know little r is, I didn't use that expression up there, so I figured I'd tell them what it is. This is the magnitude of the electric field. I think that's it could be considered self-evident. I'll go ahead and put it in. Magnitude of electric field. This is the Coulomb constant. And I think everything's pretty straightforward. So I think I've actually got it. I'm going to do a Control S, make sure that baby's still working. So that was that one. I think I'll do the one where we kind of know the answer. And let's see. Yeah, up to 9,000 at 0.1 meters, and then it plots all the way out to 0.3 meters, and it looks like it's dying off like 1 over r. I think that looks good. So I want to look at this, make sure I did what it says to do. 2 arguments, total charge, that was the capital Q and the radius of the sphere, as a function of the distance r from the center of the sphere. Yeah, I guess little r was defined in the problem statement. That didn't hurt to tell people what it was anyway. So how did I write that anyway? Little r, distance out from center. I think if people have read what my function description is, or read what your function description is anyway, they'll have a good idea what that means, distance out from the center. So it's from the center of the ball of charge. Complete algebraic solution. Yeah, I was tempted to just say, well, we solved that. I forget whether it's in class or in the book, but we definitely solved that. But I decided, nope, let's go ahead and give the full Gauss's law solutions, more than algebraic. It's got integral signs in there. Then for each function, an outline of the steps. I know I did that. So there's only one function, and there it is. Reasonable attempt at writing the program consists of a .m file. That's cool. Does it work properly? Do what it's supposed to do. It results in nothing being printed. I think nothing is printed in my case, even if I don't have the semicolon, but just to make sure that nothing is printed with the semicolon. So no, all I get is the graph. The graph comes out, but nothing's printed. So I think I've definitely got that covered. You gotta have your name in it. Yeah, I was kind of late putting it in there, but I got that in there. Must be documented. A comment saying what it does. Alright, I made a comment, but I told you, you have to say what it does. Another set of comments providing a list of arguments of the function. Got that. Input variables. Then, but I did say you got to say what it is, say what the variable is, and then if it returns. So I didn't really have to provide a list of the output variables because I got no output variables returned, but I did make a note to the reader to tell them not to expect anything. For the case of a function that includes segments, they're not self-explanatory. I did put down some names of variables. So I did a little bit of explicative work, but not very much. And then for a function that produces a graph, the graph and axis must be properly titled. I got that. Took care of that. Let's make sure it does say properly. Let's make sure I got the units in there for the axis titles. Magnitude of the electric field in newtons per coulomb. So it's supposed to be force per charge. You give me the charge in coulombs and multiply it by the force per charge, and it comes out in force. And yeah, I got that. And then the distance out from the center of the ball of charge in meters. So yeah, I got the units on there. And then what else I want? Attribution. Alright, so I didn't write the full attribution. Obviously you're not going to copy mine, because mine just tells you to tell me a story, tell me how it came about. And so I think I'm done. Go ahead and make sure the latest version is saved. I'll click save, and then I'm going to get rid of the graph. Make sure it comes up when I run it. So here I keep on using the same values. Not very interesting, but it seems to be working. Nothing got printed to the screen. So I'm going to call that a wrap for project 6, video number 3.